Hi. So we're going to start now with section 4.3. We finished the theory of linear ODE. In 4.1, 4.2 we saw a method how from one solution I can get another solution for a second order equation. Now 4.3 we'll learn how to solve the easiest, like we can say the easiest form of linear equation, which is linear homogeneous ODE with constant coefficients. But before doing that, I need to do a small review about complex analysis because, my experience when teaching this course, that not all students have know well their complex analysis. So just a review on complex numbers. Let's say complex numbers are of the form z equal a plus bi with a, b real numbers. Like example, I have z equal 2 plus 5i, z equal minus 1 plus I square root of 2. These are complex numbers. Okay, now there's something. So real of z, the real part of z is a, and the imaginary part of z is b. So if I want to show this in R2, this is a, this is b, this is the real part axis, this is the imaginary part axis, and this is my complex number c. Okay. Now the modulus of z, so the modulus of z, which is the length of this vector of coordinates ab, is equal to square root of a squared plus b squared. Now the argument of z is the oriented angle between the the oriented angle from the x-axis, from the positive x-axis to the vector AB. So this is my theta. This is the argument. The argument of z, let's say, yes. So I have let's call theta. Let's call theta to be the argument of z. Then I have cosine theta. Cosine of this angle is real part. Well, it's a over square root of a squared plus b squared, and this is the real part of z over absolute value of z. And sine theta similarly is b over square root of a squared plus b squared, and this is the imaginary part of z over absolute value of z. Now the conjugate of z, so the conjugate z bar of z is z bar equal a minus bi. So if you want to see geometrically, it is a point symmetric to z with respect to the x-axis. So if this is z, then this will be my z bar. Same real part, but the imaginary part is multiplied by minus. Now notice that z plus z bar over 2 is equal to what? If you have a plus bi, so this is a plus bi plus a minus bi over 2. This is equal to a. So I get that real part of z is equal to z plus z bar over 2. What about, how do I get the imaginary part, which is b? So this will be z minus z bar over 2i, because I got here a plus bi minus a minus bi over I. This is equal z minus z bar. Well, this is equal to 2bi over 2i, and this is equal to b. Okay. Now, given a complex number, z, I can, with argument theta, remember I can write z as a plus bi, but now a, which is here, is absolute value of z cosine theta from this formula. So this is equal, z is equal absolute value of z cosine theta, and b is absolute value of z sine theta, also multiplied by I, and z is absolute value of z cosine theta plus I sine theta. Now, if you remember from 201, that cosine theta, the power series of cosine theta is 1 minus theta square over 2 factorial plus theta cube over 3 factorial minus theta 4 here over 4 factorial minus theta 6 over 6 factorial plus, and this is equal summation from n equals 0 to infinity minus 1 power n times x power 2n over 2n factorial. Okay. What about sine theta? Sine theta is equal theta minus theta cube over 3 factorial plus theta 5 over 5 factorial minus theta 7 over 7 factorial plus. So what is really cosine theta plus I sine theta? So it will be 1 plus I theta. Now theta square, I can write minus theta square as I theta, the whole thing square. Do you agree? So this thing will be plus I theta square over 2 factorial. What about minus? Okay. Now what about minus I theta cube? I can write this as I theta, the whole thing cube. You can see it from here. So this is plus I theta cube over 3 factorial. What about now? I want to take this term. What about theta 4? This is I theta power 4. Remember, I square is equal to minus 1. So this is plus I theta 4 over 4 factorial. Continue doing this, and you still notice that this is summation from n equal 1 to infinity of I theta power n over n factorial, which is e to the I theta. Because remember, e to the x is summation from n equals 0 to infinity x power n over n factorial. This is for x real. But I can define for x complex, for z in complex, I can define e to the z to be summation from n equals 0 to infinity of z power n over n factorial. And here my z is I theta. And I get the famous formula, which is, remember, z is absolute value of z cosine theta plus I sine theta, and this is equal absolute value of z e to the I theta, where absolute value of z is a modulus and theta is the argument. So what about z bar? Z bar is the opposite of the, it is a symmetric of z. So the angle here is minus theta, but same length. So this will be equal absolute value of z bar e to the minus I theta, but same length. Absolute value of z bar is the same as absolute value of z e to the minus I theta. Okay. Now notice that I know that cosine theta, well, I know that the real part of z also, I know that the real part of z equals z plus z bar over 2. This I proved. But what is the real part of z? Is absolute value of z cosine theta. What about z plus z bar? So this is e to the I theta plus e to the minus I theta. Well, to be absolute value of z plus absolute value of z over 2, and we got that cosine theta, this is Euler formula, e to the I theta plus e to the minus I theta over 2. And similarly, sine theta, which is equal to what? Which is equal to imaginary part of z over absolute value of z, and this is equal e to the I theta, well, imaginary part of z over z, which is z minus z bar over 2i absolute value of z, and sine theta then will be z is absolute value of z e to the I theta minus absolute value of z e to the minus I theta over 2i absolute value of z. I'm assuming z is different than 0, by the way, otherwise you're dividing. And sorry about that. So sine theta is equal e to the I theta minus e to the minus I theta over 2i. And this is a complex number. I need to know how I got this formula, and you need to be familiar with Euler formula, definitely. Okay. Now, now another definition. Given D in R, so a domain in R, a complex valued function is a function y from D, so the domain is in R, but it gives me a complex number. So what is the image of x? So for x in D, I get a real, the image of x is a complex number, which is a real part, so it will be y1 of x plus I y2 of x, with y1, y2 are two functions from D to R. Okay. And this is a complex valued function. We say that y is continuous if and only if y1 and y2 are continuous, because I know what continuity in R mean. And we say that y is differentiable if and only if y1, y2 are differentiable. By the way, the interesting course in mathematics in AUB about complex analysis, which is Math 227, where you're gonna see, I mean, the whole analysis of complex numbers. Okay, y1, y2 are differentiable, and y prime of x, what's the derivative of a complex valued function, is y1 prime of x plus I y2 prime of x. And how to differentiate this one, because it's a real valued function, this is a real valued function. And now I will end with a theorem or a lemma. Now, given a linear ODE with real coefficients, very important that the coefficient should be real, of the form, well, a linear homogeneous ODE, y of x, so an of x, y of x plus an minus 1 of x, well, nth derivative, nth minus 1 derivative plus of x plus a1 of x, y prime of x plus a 0 of x, y of x, this is equal to 0. So here I'm saying that a0, a1 up to an are real valued, very important function. I mean, all ODE you're going to see here are ODE that have coefficients that are real, okay? In this course, I mean, all the coefficients are real. And I need to find real solution, okay? I need to find real solution to ODE. But assume, so suppose that y of x, which is equal y1 plus I y2 of x, is a complex valued solution, i.e. L of y, L of y1 plus I y2 equals 0. Meaning I plug in, I know what's the derivative of complex function, and I plugged it in and I found a complex solution, but I don't want a complex solution, I want a real solution. So the theorem tells me the following: then y bar, which is y1 minus I y2, is a solution. y1 is a solution, and y2 is a solution. Okay. Okay. This property is not necessarily true if my coefficients are not real. Okay. So let's see why. So I have an of x yn plus a1 x y prime plus a0 of x y equal to 0. This implies that an of x yn plus a1 of x y prime plus a0 of x y equals 0 with a bar. But now I use that an and an is real. So this means an of x yn bar plus a1 of x y prime bar plus a0 of x y bar equals 0. If my coefficient were not real, then I should have written here a0 bar. But since a0 is real, so a0 bar is the same as a0. And this implies that y bar is a solution. Okay. Now by linearity, y1, which is y plus y bar over 2, is a solution, and y2, which is y minus y bar over 2i, is a solution. So a complex valued solution gives me two real solutions. Okay, this is what is the same. Now I'll stop the video here, and this is the end of the review, and we're gonna go and start now with how to solve second order ODE with constant coefficients.